Students, welcome to the first session of our third module. So we have completed two modules. The first module was basics of compressible fluid flow, and second one was dealing with isentropic flow or flow with area change, right? Flow with area change. So that two module we have completed, and in the previous in the last module we have studied the isentropic flow. There's the area with area change. We have concentrated on nozzles and diffusers, right? So students, and this module deals with normal shock wave. Normal shock wave. So this is very important concept. This is a continuation from the previous module. The final concept we have dealt with in the previous module was over expansion and under expansion in nozzles. Okay, so hope you have understood that concept. In that I have told you that suppose there is an over expansion in a nozzle, a converging diverging nozzle. Suppose the pressure at the exit. Suppose this is the exit of converging divergent nozzle. So the pressure at exit is PE. Okay. Suppose the outside pressure, ambient pressure is PA. Okay. So there may be chances such that the fluid discharge to the atmosphere, the fluid is getting discharged to the atmosphere where the PA is such that PA is less than PE. Sorry, PA is greater than PE. The atmospheric pressure is greater than the exit pressure of the nozzle, right? So in such case, what is happening? What will be the velocity Mach number here? Mach number will be greater than 1. The flow will be supersonic. So a supersonic flow is getting discharged into atmosphere such that the pressure of the atmosphere is greater than that of the pressure at the exit of the nozzle. So will it be possible? Will it be happening in a normal way? If a flow from lower pressure to higher pressure, will it happen in a normal method? No, there will be some compression waves happening in that particular state. So I will tell you. So from here, pressure PA. This is pressure PA, PE. So discharge is happening to this particular pressure. PA is greater than PE. So when a supersonic nozzle discharges into a region where the pressure is too high to allow the supersonic flow to continue as it is. So in order to allow supersonic flow to continue as it is not that possible. But what will happen? The flow will experience a discontinuity. So if the supersonic flow has to be maintained as it is, the pressure should be lower than the exit pressure. Okay. If suddenly there is a pressure, suddenly it encounters a higher pressure, means there will be a discontinuity in the flow, and the flow will be suddenly changed into subsonic speed. So at that location, the flow gets converted from supersonic to subsonic with abrupt change in fluid properties. So that is very important. There will be a discontinuity will change an abrupt change. Okay, an abrupt change. There will happen an abrupt change in fluid properties. So in the previous module, we have studied steady flow process. We were analyzing steady flow process. The fluid properties vary in a smooth and continuous manner, but in some conditions, such as I mentioned in the mentioned now, like discharging a supersonic flow into a higher pressure. So in such conditions, there will be some discontinuities in the flow. So, those discontinuities uh, will make some abrupt changes in the fluid properties. Okay, the supersonic flow will get converted into a subsonic flow because pressure is getting higher. Pressure is getting higher means somewhat a compression process. A compression process means velocity will be reduced. So supersonic flow will be converted to subsonic flow. Okay, so that is the idea of that is the idea of shock. So what is shock? So what is happening here due to this discontinuity is nothing but compression. A compression wavefront is formed. A compression wavefront is formed because the flow is getting compressed and the supersonic flow will be converted to subsonic. So compression wavefront is formed at that location. Very important, this compression wavefront. So what will be accompanied with this compression wavefront? It will be accompanied with the pressure rise and abrupt change in other fluid properties. Okay, so it will accompany with pressure rise because lower pressure to higher pressure rise and abrupt change in fluid properties. Okay, fluid properties. So this phenomena is described as shock wave. This phenomenon is known as shock wave. Okay, so a shock wave is a special kind of pressure wave. So it is a shock wave is a pressure wave, compression pressure wave. A compression pressure wave with a steep pressure rise. So a compression wavefront in a supersonic flow field and the flow across the wavefront results in abrupt change of fluid properties, right? So since this shock wave is more or less an instantaneous compression of the gas, it cannot be a reversible process. So that is very important. Shock wave is irreversible process. Shock wave is irreversible process, very important because this is happening instantaneously, right? So this is an instantaneous process. All the instantaneous processes are irreversible only. It won't be reversible. So we cannot identify those processes as isentropic process because isentropic processes are reversible process, right? So shock wave is an irreversible process. So the kinetic energy possessed by the incoming gas is utilized for the compressing the gas across the way. Okay, so since the shock wave is irreversible, the kinetic energy of the gas leaving the shock wave must be lesser than the isentropic compression between the same pressure ring. So have you understood it? So this is PE, this is PA, and while discharging to the atmosphere of pressure A, some shock wave is happening. So the gas is getting compressed to PE to PA compression, right? So while compressing, the kinetic energy possessed by the incoming gas is utilized for the compressing the gas across the wave, right? So this here, if this is if this section is 1, this section is 2. Okay. So from section 1 to section 2, P1 to P2 compression is taking place. Okay. So in between that there is a shock wave. So kinetic energy here is 1, kinetic energy in the second section is 2. So KE1 will be greater than KE2. Okay. Because there will be a loss due to for which the kinetic energy will be somewhat utilized for compressing the gas. So there will be a loss of kinetic energy, right? uh, and suppose between the same pressure limit, P1 to P2, compression is taking place, isentropically. So isentropic compression, no shock wave. Shock wave is irreversible, right? Suppose I am compressing from P1 to P2 isentropically, so that is a reversible process. Then KE1 and KE2 in this case, so here isentropic process. So KE2 isentropic will be greater than shock in the case of shock wave. So KE2 isentropic will be always greater than Ke2 in the case of shock wave. Why? Because shock wave is irreversible process. Isentropic process is a reversible process. So in case of irreversible process, the loss of kinetic energy will be higher. So the kinetic energy of gas leaving the shock wave is must be lesser than that for an isentropic compression between the same pressure limits P1 and P2. Okay. So these are basics. These are basics about a normal shock waves. So why? What is the reason for this reduction in kinetic energy? Because it is this losses associated, because of the losses associated with the shock wave. Because this kinetic energy will be used in heating of the gas to a static temperature above that corresponding to the isentropic compression value. So the temperature in the case of isentropic compression will be lesser than that of the case in the lesser than in that case of shock wave. So T2 in case of shock wave will be greater than T2 in case of isentropic compression. Okay. So this kinetic energy, this extra kinetic energy, so this loss in kinetic energy will be used to increase the temperature, static temperature of the shock wave, the gas after the shock wave. Okay. Now we will learn about types of shock wave. Types of shock wave. Okay. Students, there are mainly two types of shock wave. Actually, shock wave is a type of phenomena that occurs in supersonic flow only. Okay, supersonic, mainly it occurs in supersonic flow. Okay, but all wave phenomena may not result in shock waves. If the wave phenomena are classified according to the strength, okay, based on strength of the wave, there are two types. One is weak wave and another is shock wave. So according to the wave strength of the wave, we can classify the wave as two types: weak wave and shock wave. Okay. So what is weak wave? Weak wave is those type of suppose there is a conduit, a flow is happening. Okay. So suddenly a turning is encountered while in the flow path. If there is some turning, suppose here the Mach number is greater than 1, a supersonic flow. This supersonic flow encounters a turning at somewhere in its path. If this turning is concave means this turning is concave, right? This is concave, this is convex. So there are two types of turning, concave and convex. So this is a concave turning. If this is the flow is turned like this, if a flow is turned like this is a convex turning. Okay. Suppose this is a concave turning, then after the turning, suppose this is M1 section 1, this is section 2. So here M2 will be less than M1. Okay. So this M2 will be lesser than M1 in case of concave turning. Uh, so this type, there will be a wave generator. So this generated wave will be compression wave. Compression wave. So in case of concave turning, a compression wave. Compression means because the Mach number is getting reduced, or the velocity of fluid is getting reduced. Velocity is getting reduced means pressure is getting increased, or there is a little bit pressure rise encountered, means that the flow is getting compressed. So the wave that is formed while the sudden increase in pressure, due to the turning of the flow is known as a compression wave, and this wave is a weak wave. This wave will be a weak wave because the pressure rise is not that much higher compared to the case we have considered in the case of that expansion, under expansion, or over expansion in the nozzle. So this type of wave is considered as weak wave or Mach wave. This is also known as weak wave or Mach wave. Weak wave or Mach wave. So this wavefront increases the pressure uh, in case of concave turning, and in case of convex corner, suppose this is the theta, so flow is getting turned like this. Here, if this is M1 and here it is M2, so M2 in the case of convex M1 will be greater than 1 only, and M2 will be greater than M1 in case of convex turning. So here what is happening? The Mach number is getting increased, velocity is increased, and if velocity is increased means pressure is decreased. Pressure is decreased means some expansion wave is happening. Expansion wave. Because pressure is decreased. Pressure decreased means an expansion wave is formed. So this is another weak wave. Waves due to turning turning of the flow are weak waves, and they can be either compression waves or expansion waves, depending upon the type of corner. If it is a concave, it is compression wave. If it is if it is convex turning, it will be expansion wave. So these are these type of waves are called weak wave or Mach wave. So since for the above two cases the flow deflection angles are infinitesimal, the waves generated are considered weak, and we can apply here isentropic analysis. So isentropic analysis can be applied in case of in case of weak waves. So this isentropic analysis holds good in case of weak waves, because there is no that much higher pressure rise, or the wavefront is not that much instant. It can be assumed as a little bit a reversible process. That is why those waves are called weak waves. So we can apply isentropic analysis. But on the other hand, a shock wave can only be compression type. Okay. So the shock wave we have already learned. The other type of based on strength, shock wave, higher strength, higher strength, only only compression, only compressive type. So in case of shock wave, pressure is always increased. The shock waves are accompanied with a steep rise in pressure. So expansion waves are not possible in case of shock waves. So every time a shock wave is happened means the wave is a type of compression. Okay, the expansion shock is not possible because expansion in an adiabatic process requires a decrease in entropy and all. Don't worry about it. You just understand for the time being that an expansion process, an expansion shock is not possible in case of shock wave. Okay, so there is no expansion shock waves. There is only compression shock waves. Okay, and another classification based on, so based on strength we have studied, based on uh, sorry, we can classify based like stationary and stationary shock wave and moving shock wave. So there are based on the mobility of the shock wave, we can classify it as stationary shock wave and moving shock wave. So students, what is stationary shock wave? Stationary shock wave is a shock wave is stationary. So stationary shock wave means it is as the wave is shock wave is stationary. Stationary when the gas in which it propagates, when the gas in which it propagates travels at a speed equal to that of shock, travels at a speed equal to shock wave. So the shock wave is also traveling. The gas in which this shock wave propagates also travels with the same speed, but in opposite direction. In opposite direction. So both shock wave and the gas both are traveling with the same speed but in opposite direction. So such shock waves are called stationary shock wave. So such shock waves can occur in convergent, divergent nozzles, diffusers, etc. Okay. And what is moving shock wave? Moving shock wave is that shock wave when the shock wave travels in a stationary gas. Stationary gas. So the medium or the gas is stationary, or gas is moving with low velocity, or gas is moving with low velocity. Low velocity. Then the wave becomes a moving shock wave. So such case, the shock waves are known as moving shock waves, because only shock wave is moving. The gas the gas or the medium is stationary or moving with a very low velocity. Such case, shock waves are called moving shock waves. And the stationary shock wave may be either attached to an object or detached to an object. So suppose this is an inlet of the diffuser. So this is an inlet of diffuser. So Mach number is greater than 1. This diverging section can be considered as a diffuser, right? Sorry, this cannot be. If Mach number is greater than 1, it is not diffuser. Okay, don't worry. Don't worry about the Mach number and all. If this is an inlet of a diffuser, there may be some. If the shock is attached to the this diffuser, this means it means this is a attached shock. If this is an inlet of diffuser and shock is somewhat here, so there is a gap between inlet and the shock, and this means detached shock. So this is detached shock, this is attached shock. Okay. And another classification of shock wave is based on the angular position. So suppose this is a shock and this is the flow. If this is 90 degree, this means normal shock, perpendicular to the flow, normal shock wave, okay. And if this is like this, and it is not perpendicular, it is positioned at an angle, at a particular angle. So it is positioned at an angle means this type of shock is known as oblique shock wave. So if it is perpendicular, it is known as normal shock wave, and if it is at a particular position at an angle to the flow direction means it is oblique shock wave. So students, in this uh, in this module we are dealing with normal shock waves. So what are shock waves? We have already studied what is a shock wave. Shock wave is a type of wave which has got higher strength. The waves with the lower strengths are called weak wave or Mach wave. So those shock waves which are positioned at a right angle to the flow direction are known as normal shock wave. So in case of normal shock wave, we can analyze using one-dimensional flow equation. But in case of oblique shock, we may need to analyze it two-dimensionally. So it will be a little bit complex. So here we will apply our one-dimensional equations. Okay. So before that, we have to. So before going to the analysis of shock waves, we may simply specify some of the general characteristics general characteristics of normal shock wave. Okay. So first one is shock wave is perpendicular. Shock wave is perpendicular to streamline. So that is why it is known as normal shock wave. Okay, perpendicular to streamline. Second one is shock wave is so thin. Okay, so it is not a thick wave, it is a thin wave such that it can be considered to takes place at a constant area, at a constant area, okay. I'll be explaining all those points while derivation and all. So we will be deriving some governing equations and all. So you will be getting a detailed understanding of these concepts. So third assumption is that the boundary surface of the third assumption is that the flow is considered to be frictionless. Flow is considered. So in the analysis of shock wave, the flow is considered frictionless. So there is no friction in the flow. Fourth one, the flow in the stream is adiabatic. Flow is adiabatic means there is no heat transfer, but it cannot be considered as isentropy because the normal shock waves are irreversible process. So it can only be considered adiabatic, but it cannot be considered isentropy. So what does it mean? There is a change in entropy. So an entropy change is happening across the compression wave or this shock wave. So if the flow was isentropic, there won't be any change in entropy. The entropy would have remained constant. And fifth one is there is no external work. So no work, no heat transfer. Okay. So no work, no external, no heat transfer, and body forces are negligible. Body forces are negligible. So these are the assumptions that should be applied in case of the study of normal shock waves. So students, with this, I think we can conclude this session. And the next session, we will be going to derive all the equations necessary for the analysis of our shock waves. And based on that equations, we can do problems for this particular normal shock wave. So please try to remember all this. So please note all these general characteristics or assumptions that we will be applying in the analysis of waves. Sorry, normal shock waves. So according to this assumption only, we will be simplifying all the governing equations. So the governing equations can be simplified based on these assumptions. So why are we applying these assumptions? Means in order to simplify the governing equation so that we can easily solve the problem. Okay. So with this, we will stop. Thank you.